So thanks a lot for the introduction, and thank you. I thank the organizer for giving me the opportunity, and of course ICTS for the nice hospitality. At the onset, I'd like to acknowledge funding sources and computational facility, and also contributions from our experimental collaborator Shiva from IIT Kanpur, who is here. So who is probing some of the aspects that we are going to discuss today experimentally. So, the aspect that we are going to discuss about is called hydrodynamic entrampment. So this is a real experiment where bacteria are released just on above a substrate. They go into the substrate and then they get trapped and they move only along the substrate. So, so how that process happens is not fully understood, but it is interesting for application point of view. For example, if the bacteria carry some kind of drug to treat something on a substrate, then you want them to go to the substrate and get trapped. On the other hand, if you don't like the bacterial infections, then you actually would like to prohibit them to get trapped. Okay, so this is another example where bacteria are put in a solution which is kept between two substrate, and here is a concentration profile of the bacteria along this length. So you can see that the bacteria accumulate near the substrates. So the bacteria that I talked about are examples of flagellated active particle. So specifically E. coli. This is a real example of them, and this is a simulation from our group. This has basically a flagellar bundle which is flexible and is behind the cell body, and there is a cell body which is fairly rigid and in front. Similar physiological, I mean, those aspects are also found in different bacteria. The basic mechanism it uses to swim is the following. So the flagella pushes the fluid backwards. As a result, the thrust force, I mean the reactional force is applied on the cell body, because of which it's moved forward. So when it swims, it creates disturbances in the fluid, and the interaction between two swimmers, or interaction between swimmer and a substrate through these disturbances, is what we call hydrodynamic interaction. To capture that, we need to calculate the disturbance around the swimmer. The simplest model to do that is to replace the swimmer with an equal and opposite set of forces, which is called stress sled. The flow field of that object and this object will be similar if you are far away from that. So when you start approaching it, then you will be able to see the extended nature of the cell, but the extended nature of the flagella and so on. So that's why this is the first step, the minimal model, but it's a very powerful model. So for example, the famous active stress that we all know about is worked out, the form of that is worked out by considering stresslets at its position, at the location of each particle, and then averaging their effects. So another example is that even in this experiment, so if you assume that each bacteria is a stresslet like that, then the interaction with the wall make the stresslet align parallel to the wall. And once that is done, then the induced velocity on that object will be towards the boundary. So hence the bacteria are actually pulled towards the boundary. And that is the consideration that leads to this continuous curve, the theoretical plot. Okay, so that works not so bad. So even then we talk about in this talk, I mean, taking steps beyond and see what's there. Okay. So a few years back, what we did, we introduced an extended cell body, okay, here in the model. The flagella is still a point force. One aspect of that is that now we have to consider respecting the boundary condition on the surface of the cell body, that you can do by introducing image singularities created by the sphere of this point force that lies within the sphere. So that is a point object at this, the location is a point, but there is a series of objects that you have to put in. So then in a different context, in the bulk, when you talk about dense systems, or when you talk about putting the swimmer in a imposed flow, direct in my group, so that you need further modifications, those are necessary. So for example, you can actually distribute the point forces along the flagella. You can have a physical flagella in the form of a slender rod. You can also allow buckling of the flagella. Okay, these are some of the things, and at the end, the full model gives us this flow field, which is, you can see that it's drastically different from the simplified model where the physical flagella is not there, which in turn is much more difficult to solve from the axisymmetric counterpart. So even that the effort was worth it, because direct when you put the swimmers in a flow, we found some interesting results that we discussed here, I mean, a couple of times, even last year. So the essence of the model is that we have a slender rod here, which is the flagellar bundle. So it offers friction to the entire assembly. So the effect on the rod and effect due to the rod is obtained by integration done over entire rod. Apart from that, there are flows of different components which are actually captured in these blue terms. So I mean, one word of caution is that suppose we include the friction from the rod, but we don't include the flow due to the movement of the rod. So that was kind of the model that was studied by other people in other contexts. And when we plotted the flow field of that object, we found that it's just a Stokes slit. Okay, it's not a stress slit. So for our case, that will be an oversimplification. We do need to actually include the effect of the flow due to the flagellar movement. And that is done by introducing the Stokes slit, which are actually calculated by averaging over the velocities over each segment of the rod. The velocities are in turn the solutions that we want. Therefore, this makes the model really incredibly hard to solve. It has to be done self-consistently. But on top of it now, for the current problem, Ambaris wants to put that model near a substrate. Now, the model has become much more complicated. You have to respect the boundary condition not only one surface, but on two surfaces simultaneously. And just to give you a hint how difficult is that, so if you would have just a point force for the flagella, so you would have to calculate like 21 singularities down the wall. Okay, but imagine doing that for the entire rod, and then you have to do that self-consistently. That is the kind of problem Ambaris has solved. Now, another point of caution is that the models which are at our disposal are these two. So this is the one where we talk about distributing the point forces, but there is no physical flagella. And this is the full model that I just talked about. Both of their far field are as expected as that of a stress slit. Okay, this is how much time is left? Oh, 30 seconds. Okay. Oh, okay. So okay, then I quickly move. I mean, so just okay, just to give you the result. So once we do the full analysis, what we found is that the distributed model gives a wrong result. I mean, it actually points the bacteria points down towards the wall, which will overestimate the concentration there. So you do need to consider the full model. Just 30 seconds more. Okay. So then in order to get the experimental observation, but what you, on top of it, you get that the bacteria very close to the wall, they point towards the wall, suggesting an active wall entrampment, which was missed by the stress slit level. Okay. And we also, if you consider full model, we also found that the wall entrampment is much more enhanced compared to the stress slit assumption that we did earlier. So I mean, we have more prediction, but due to in the interest of time, just concluding.
Any questions?
Entrapping depend on the nature of the surface of the wall. I mean that shape of the wall or something.
So the shape of the wall, of course, it will matter, because then it will change these image singularities. So far we have only considered flat surfaces.
Okay.
And the nature of the wall, we have actually, for many solid surfaces, it has to be solid surface, many solid surfaces, stick boundary condition, which is the condition that the velocity goes to 0 on the surface, is valid. So for those surfaces, the results will stand.
I see. Okay, thank you.